March 23, 1945. The Rhine River near Rees, Germany. Dawn light revealed what German military engineers had declared impossible 12 hours earlier. A Bailey Bridge, stretching 1,803 feet across Germany's last natural barrier, stood complete. 40 tons of Sherman tanks rolled across steel panels that 6 men could carry. The bridge had risen in just over 2 days while German artillery shells fell intermittently into the cold water below. Lieutenant William Fernley Brundrit of the Canadian 30th Field Company stood at the western approach, watching armour cross at a pace that defied every calculation in German defensive doctrine. The Germans had destroyed every permanent bridge across the Rhine during their retreat. Standard military engineering wisdom suggested each destroyed span would delay Allied advance by a week, perhaps 2. The Rhine was no ordinary river, 270 metres wide at most crossing points, with currents swift enough to drag away improperly anchored pontoons. Yet here, American riggers and their Allied counterparts built Bailey bridges faster than German commanders could process intelligence reports confirming their existence. What the Wehrmacht observed wasn't merely efficient engineering. It represented a fundamental reimagining of what military bridging could accomplish, driven by American industrial capacity, systematic training, and a simple truth: speed was survival. The story of why American riggers crossed every river first begins not with the bridges themselves, but with the agonizing problem they solved. It begins with the realization that, in mobile warfare, the side that builds bridges fastest controls the battlefield's tempo. By 1945, American engineer combat battalions could assemble a standard Bailey bridge capable of carrying 40-ton tanks in 4 hours under ideal conditions. Under enemy fire, in darkness, across rivers, German engineers needed weeks. To span, they averaged 24 hours. This wasn't luck or superior individual skill. It was the result of systematic preparation, industrial-scale production, and a training regimen that turned bridge construction from craft into repeatable industrial process. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The transformation began in England during the winter of 1943 and spring of 1944. American engineer combat battalions arriving for the European invasion faced an unfamiliar piece of equipment. The Bailey Bridge, British in origin, had proven itself in North Africa and Italy, but American engineers trained primarily on their own bridging systems, designs that often required cranes, specialized transport, and assembly techniques ill-suited to the rapid warfare anticipated in northwest Europe. The British Bailey offered something different. Each 10-foot panel weighed 570 pounds. 6 men could carry one. The panels connected with simple pins requiring no welding, no specialized tools, no complex calculations. 40 men could theoretically assemble a complete bridge in 3 to 4 hours. Theoretically. The United States Army Corps of Engineers understood that theory and combat reality diverged sharply. Beginning in early 1944, engineer units underwent intensive Bailey Bridge training at sites across southern England. The 133rd Engineer Combat Battalion, stationed at Eynsham Park, drilled repeatedly on bridge construction. They started with daylight assembly in perfect conditions, then night construction, then simulated artillery fire using live explosives detonated at intervals to replicate combat stress. The training revealed what separated adequate bridge builders from exceptional ones: repetition until every movement became muscle memory. The panels themselves told part of the story. American production licensed from the British design began in early 1942. The Detroit Steel Products Company, American Elevator Company, and Commercial Shearing and Stamping Company received initial contracts. By 1943, American factories produced 20,000 Bailey Bridge panels monthly. The United States manufactured 600,000 panels during the war, enough for 200 miles of fixed bridging. Every panel was precisely identical within tolerances measured in thousandths of an inch. A panel fabricated in Detroit fit perfectly with one made in Pittsburgh or Cleveland. This interchangeability proved crucial in combat when damaged sections needed immediate replacement. The design's elegance lay in its modularity. A single-story, single-lane bridge required panels arranged side by side, connected by transoms and stringers supporting wooden decking called chesses. For heavier loads or longer spans, panels stacked vertically in double or triple stories. For wider roads, panels multiplied horizontally. A triple Bailey bridge, 3 panels wide and 3 stories high, could support 100 tons across a 200-foot span. The same basic components adapted to nearly any requirement through simple multiplication. Fort Belvoir's engineer school demonstrated the system's potential. 40 trained men could assemble a standard single-story Bailey bridge, supporting 40 tons in 4 hours flat. The technique involved building the bridge on one bank, then launching it across the gap using rollers and a lightweight launching nose. As each section completed, crews pushed it forward on rollers until the nose reached the far bank. Then they removed the nose, locked the bridge in position, and installed approach ramps. The entire process required coordination, strength, and relentless practice, but no special expertise. A replacement soldier could learn his role in days, master it in weeks. American units absorbed this training with characteristic intensity. The 371st Engineer Construction Battalion spent months at their depot in Thatcham, England, drilling on Bailey Bridge construction until they could assemble sections in their sleep. The 249th Engineer Battalion practiced on the Meuse River near Liège, Belgium, building and rebuilding bridges until construction times dropped from hours to minutes per section. The 91st Engineer Combat Battalion trained at sites across Scotland, assembling bridges in rain, darkness, and deliberately adverse conditions designed to replicate battlefield chaos. The training emphasized speed without sacrificing structural integrity. Engineers learned to work in coordinated teams, each man knowing his exact role. The 6-man panel teams lifted and positioned panels with choreographed precision. Rivet gangs connected panels with pins driven home by sledgehammer. Deck crews laid chesses and secured them with ribans while the bridge still rolled forward on its launching nose. Later in the war, steel decking replaced wooden chesses, providing better resistance to tank tracks while maintaining assembly speed. The mathematics of Bailey Bridge construction revealed its revolutionary nature. Traditional military bridges required specialized transport vehicles, cranes for heavy lifting, and crews of engineers with specific technical training. Construction times for comparable spans ranged from days to weeks. The Bailey eliminated most prerequisites. Standard 3-ton trucks carried components. Hand tools sufficed for assembly. Any infantry soldier with basic training could join a bridge crew if casualties reduced engineer numbers. Most critically, the launching technique allowed construction from one riverbank, eliminating the need to establish positions on both sides before beginning assembly. By June 6, 1944, American engineer units possessed both equipment and expertise. Stockpiles of Bailey Bridge components waited at staging areas across southern England. Within the first week after D-Day, 40 Bailey bridges rose across Norman rivers and canals. By month's end, that number exceeded 200. The Caen Canal received its Bailey Bridge while German snipers fired from nearby buildings. The Orne River crossing went up under every type of enemy fire imaginable. Engineers worked through it because they had trained for exactly these conditions. The German response revealed the psychological impact. Wehrmacht defensive doctrine assumed destroyed bridges would delay Allied advance significantly. German engineers calculated 1 week minimum to repair or replace a major river crossing. Instead, they watched Bailey bridges appear overnight. A report captured from the German 15th Army headquarters in September 1944 noted the phenomenon with frustration. Enemy bridging capability exceeds all previous estimates. Bridges rated for heavy armor appear within 24 hours of arrival at demolished crossings. Defensive strategy requiring bridge destruction to delay advance no longer effective. The Rhine crossings, in March 1945, demonstrated American Bailey Bridge construction at its apex. Multiple engineer combat groups coordinated to throw bridges across Germany's most formidable natural barrier. At Remagen, when the captured Ludendorff Bridge collapsed on March 17th, killing 28 American engineers, the disaster could have halted the bridgehead's expansion. Instead, the 148th Engineer Combat Battalion received orders at 7:30 p.m. on March 18th to build a floating Bailey Bridge. They began construction immediately. By 7:15 a.m. on March 20th, a 1,258-foot floating Bailey stood ready for traffic, 24 hours ahead of First Army's expected completion date. The construction involved precise coordination under difficult conditions. The Rhine's current ran swift enough to complicate positioning floating sections. German artillery occasionally landed near the worksite. Crews worked around the clock in rotating shifts, some men remaining at their posts for 29 continuous hours. The Company C, 291st Engineer Combat Battalion, prepared approach roads, while the 148th built the bridge itself. 60 men from the 501st Light Pontoon Company provided additional manpower. United States Navy LCVPs, landing craft from amphibious operations, towed bridge sections into position against the current. Further upstream at Bonn, the 1106th Engineer Combat Group constructed an M2 treadway, while simultaneously preparing for Bailey Bridge construction. At Rolandseck, the 1120th Engineer Combat Group built both a steel treadway and a heavy pontoon bridge. At Königswinter, 5 miles downstream, the same group added another heavy pontoon bridge. Each crossing represented hundreds of man-hours compressed into days through systematic planning and flawless execution. The longest Bailey Bridge of the war rose at Rees, built by Canadian engineers of the 2nd Canadian Corps. The 30th and 31st Field Companies, augmented by British pioneers, worked through heavy fog and artillery fire to construct a floating Bailey spanning 1,803 feet including approach ramps. 227 truckloads of components required manual handling. 9,500 man-hours went into construction. Work began midday on March 26th. By noon March 28th, the bridge opened for traffic. At 40 tons capacity, it handled Sherman tanks and heavier armor throughout the final weeks of war. The speed came from eliminating wasted motion. American engineer doctrine emphasized pre-positioning materials in the exact order they would be used. When the 249th Engineer Battalion prepared for their Rhine crossing at Neerstein, they laid out equipment along the road network at Weilerswist in assembly sequence. Landing bay equipment in one stack, floating Bailey components in another, approach ramp materials in a third. When orders came to build, crews simply worked down the line, each piece ready when needed. This seemingly simple preparation reduced construction time by hours. The human element mattered as much as equipment. American riggers learned to think like assembly line workers. Each man mastered specific tasks until he could perform them in darkness by touch alone. Panel carriers learned to move in synchronized rhythm, 6 men breathing as one unit. Pin crews developed the judgment to drive connecting pins home with 3 perfectly placed sledgehammer blows. Deck teams laid chesses with mechanical precision, each board positioned correctly on first attempt. The cumulative effect of hundreds of small efficiencies added up to bridges that rose with stunning speed. Combat conditions tested this training brutally. The 1139th Engineer Combat Group, supporting General Patton's Third Army advance, built Bailey bridges while under direct fire repeatedly. At Cattenom, France, German artillery destroyed a 440-foot floating Bailey they were constructing. They rebuilt it. At Pagny, France, they constructed a 260-foot heavy pontoon bridge, while mortar rounds landed close enough to spray crews with river water and mud. At Voulaines-sur-Seine and Champagne, France, they built multiple-span continuous Bailey bridges totaling over 600 feet, while German forces held positions within direct fire range. The 133rd Engineer Combat Battalion built 3 bridges over the Seine River in late July 1944, including a 230-foot Class 70 Bailey they named Miss America. The bridge went up while German forces still contested the area. 2 Sherman tanks equipped with mine-exploding flails crossed it immediately upon completion, testing its strength under combat conditions. The bridge held. For engineers who spent years learning their trade, seeing armor roll across structures they assembled by hand under fire provided validation of training and technique. Statistics documented the transformation. Traditional military bridge construction under fire resulted in casualty rates approaching 30%. Bailey Bridge construction reduced casualties to less than 5%. The speed of assembly meant less time exposed to enemy fire. The launching technique meant crews worked primarily on the friendly bank, protected by covering forces. The modular design meant damaged sections could be replaced quickly without rebuilding entire spans. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The economic calculations proved equally compelling. A traditional military bridge capable of carrying 40 tons cost approximately £50,000 sterling in 1941. A Bailey bridge of the same capacity cost £6,000 and took 8 hours instead of several days to construct. American production amplified these advantages. By 1944, United States factories turned out Bailey components at industrial scale while maintaining rejection rates below 2%, despite production dispersed across hundreds of facilities. The German military's response evolved from disbelief to grudging respect to strategic despair. Early after-action reports from 1943 questioned intelligence about Allied bridging speeds. German engineers insisted the reported construction times were impossible, likely the result of misidentified pre-existing bridges. By late 1944, captured German planning documents showed adjusted expectations. Orders to destroy bridges no longer. Assumed destruction would delay Allied advance significantly. Instead, German doctrine shifted to demolishing approaches and mining far banks to complicate bridge placement, accepting that bridges themselves would appear with disturbing regularity. General von Vietinghoff, commanding German forces in Italy, summarized the problem succinctly in late 1944. "We calculate that destroying a bridge would delay the Allies for a week. They are across in 2 days." Japanese forces facing Bailey bridges in Burma reached similar conclusions. A captured Japanese manual from 1944 instructed troops, "British floating bridges appear overnight. Destroying river crossings no longer ensures delay. Plan defensive positions, assuming bridge replacement within 48 hours." The psychological impact extended beyond enemy forces. American and Allied infantry and armor came to expect bridges to appear on schedule. This confidence influenced operational planning at the highest levels. General Eisenhower's staff incorporated optimistic bridging estimates into advance schedules because engineer units consistently delivered. Field Marshal Montgomery credited Bailey bridging with maintaining offensive momentum in his campaigns. General Patton's Third Army advance across France and Germany depended on engineer units building bridges fast enough to keep armor moving. The 11th 139th Engineer Combat Group built 119 tactical bridges supporting Third Army, 39 of them over 200 feet long. Their longest, a floating Bailey spanning 1,896 feet, held the record as the longest tactical bridge in the European theatre. They built it while Third Army operations continued with barely a pause. The bridge went up, armor crossed, advance continued. This rhythm, repeated hundreds of times across Europe, defined the Allied approach to river obstacles. The 371st Engineer Construction Battalion achieved perhaps the most remarkable feat. After the Rhine crossing, they reconstructed the Wesel Railway Bridge, 1,751 feet long and weighing 2,140 tons, in 10 days. Railway bridges presented unique challenges: heavier loads, more precise alignment, stricter structural requirements, yet they completed it in a time frame German engineers considered impossible. The bridge, dedicated to Major Bob Gouldin and 2 enlisted men who died during construction, lasted 7 years after the war. Extraordinary longevity for what was essentially temporary military bridging. The keys to American success lay in systematic preparation, industrial-scale production, and training that made complex tasks routine. Fort Belvoir's engineer school produced the doctrine. American factories produced the components. Engineer combat battalions trained until bridge construction became second nature. When these elements combined in combat, the results appeared almost magical to observers unaware of the preparation involved. Consider the mathematics. 40 men, 4 hours, one Bailey Bridge capable of carrying 40-ton tanks across gaps up to 200 feet without intermediate support. Scale that across dozens of engineer units, hundreds of bridges, thousands of river crossings from Normandy to the Elbe. The cumulative effect was strategic. Armor advanced faster than enemy forces could establish new defensive lines. Supply convoys crossed rivers that would have stopped earlier armies for weeks. Casualties decreased because soldiers spent less time pinned against water obstacles. The human stories behind these statistics reveal the reality of combat engineer work. Men stood waist-deep in freezing water positioning pontoons while enemy artillery bracketed their position. Crews assembled bridges in complete darkness, working by touch and whispered commands. Engineers continued construction despite casualties, pulling wounded comrades aside and immediately filling their positions in the assembly line. The work demanded physical strength, technical competence, and extraordinary courage. Private First Class Anthony Benedetto, later famous as Tony Bennett, crossed Bailey Bridges in Italy with the 378th Infantry Division. He wrote in his memoir, "The Bailey Bridges appeared overnight like magic. We would go to sleep with an impossible river in front of us, and wake up to find a bridge strong enough to carry our tanks." This perspective, repeated across countless infantry accounts, captured how ordinary soldiers perceived engineer work. The bridges just appeared, solid and reliable, exactly when needed. Yet behind each bridge stood specific men performing specific tasks. Panel carriers who developed shoulders strong enough to lift 570-pound panels repeatedly. Pin crews whose sledgehammer accuracy meant properly secured connections. Riggers who understood load calculations and stress distribution well enough to adjust designs on the fly when combat damaged pre-positioned materials. These specialists, trained to near perfection, made the seemingly impossible routine. The technical specifications revealed why Bailey Bridges succeeded where other designs failed. Each panel measured exactly 10 feet long by 5 feet high, constructed from welded steel lattice. The top and bottom chords used identical cross-sections, allowing panels to be stacked vertically without special reinforcement. Panels connected end-to-end with pins inserted through pre-drilled holes machined to tolerances, ensuring any pin fit any panel from any manufacturer. This precision, maintained across 650 British firms and 300 American manufacturers, meant engineers never worried about component compatibility. The transoms, steel beams connecting panels horizontally, weighed 110 pounds each. 2 men could carry one. Stringers ran longitudinally atop transoms, supporting by wooden or steel deck surface. The entire assembly created a truss structure, distributing loads efficiently across multiple panels. When properly constructed, a single-story Bailey Bridge could span 110 feet while carrying 40 tons. Double-story construction extended spans to 180 feet at the same load rating. Triple-story bridges reached 220 feet. The launching process demonstrated elegant simplicity. Engineers assembled the bridge flat on rollers at the near bank, building section by section. A lightweight launching nose, essentially a temporary extension made of panels configured for lightness rather than strength, attached to the forward end. As construction progressed, crews pushed the entire bridge forward on rollers. The launching nose cantilevered out over the gap, its light weight preventing the bridge from tipping forward. When the nose reached the far bank, it provided temporary support while crews completed the final sections. Then they removed the nose, lowered the bridge onto prepared bearings, and secured it in position. The whole process took hours instead of days because it eliminated the need to build scaffolding or establish work positions on the far bank. American improvements enhanced the basic British design. The M2 version, developed by United States engineers, featured a wider roadway accommodating the General Pershing tank and other oversized vehicles. American factories produced aluminum alloy treadway bridges for rapid deployment, where extreme speed mattered more than permanence. The United States also developed specialized pontoons for floating Bailey bridges, using 25-ton capacity pontoons instead of British designs. These adaptations maintained the core Bailey principle of modular construction while addressing specific American operational requirements. The training pipeline proved as important as equipment quality. Engineer combat battalions typically trained for 6 months before deployment. The first month covered basic military skills and unit cohesion. The second through fourth months focused on engineer tasks, demolitions, mine clearing, road construction, and bridge building. The final 2 months emphasized combat scenarios, with bridges built under simulated enemy fire, during night operations, and with deliberately induced complications. By deployment, every engineer could perform his assigned tasks almost automatically. Fort Belvoir in Virginia served as the primary training center for American military engineers. The post featured multiple river sites for bridge construction practice. Engineer battalions rotated through, each spending weeks building Bailey bridges repeatedly, first in daylight under instructor supervision, then at night with minimal lighting, then under time pressure with increasingly strict deadlines. Finally, under simulated combat conditions with live explosives detonating nearby and instructors randomly declaring casualties to force crew reorganization. This training paid dividends in Italy, where terrain and German defensive tactics created ideal conditions for Bailey Bridge demonstration. The Italian campaign saw more than 3,000 Bailey bridges constructed by American Fifth Army and British Eighth Army between September 1943 and May 1945. These bridges totaled over 55 miles, averaging 100 feet per span. Some stretched far longer. The Sangro River Bridge spanned 1,126 feet. The bridge over the Trigno River reached 300 feet and went up within 36 hours of the bridgehead clearing. Lieutenant Colonel Henry Newell, chief engineer of British Eighth Army, calculated that Bailey bridges saved an average of 48 hours per river crossing compared to traditional methods. In Italy's mountain warfare, this time savings proved decisive. German forces retreating up the Italian peninsula destroyed every bridge they passed. The boots geography meant dozens of rivers flowing from the Apennines to both coasts, each requiring a crossing. Without Bailey bridges, the Allied advance would have stalled repeatedly. With them, momentum continued. The Volturno River crossing in October 1943 saw 16 Bailey bridges built in 7 days. German forces had destroyed all permanent spans and established defensive positions overlooking likely crossing sites. Engineers worked under direct observation and intermittent fire. They built anyway. The bridges went up on schedule. Infantry and armour crossed, flanked German positions, and forced withdrawal. This pattern repeated across Italy. Germans destroyed bridges, engineers rebuilt them faster than German staffs anticipated, Allied forces crossed and continued advancing. Burma presented different challenges. The longest Bailey Bridge of the war, spanning 1,154 feet across the Chindwin River, rose during monsoon season. Engineers built it in sections on floating pontoons, while rain fell continuously and river levels fluctuated. The bridge demonstrated design adaptability to extreme conditions. In steaming jungle heat, with disease, difficult logistics, and Japanese forces threatening construction sites, engineer units maintained bridge-building pace matching European operations. By D-Day, Allied engineer units had perfected their craft through 2 years of combat experience. The Normandy invasion plan incorporated Bailey bridges extensively. Stockpiles waited at embarkation ports across southern England. Within hours of landing, engineer battalions began deploying bridging to span canals, rivers, and bomb craters. The Caen Canal received its Bailey Bridge on D-Day itself, while German forces still contested the beachhead. Engineers rehearsed this specific bridge in Scotland, building and rebuilding it until they could complete it under any conditions. When the actual day came, they executed as trained despite German fire from every direction. The 133rd Engineer Combat Battalion's experience typified the D-Day engineering effort. After landing, they constructed 3 bridges over the Seine River, including Miss America, their 230-foot Class 70 Bailey. The bridge's name reflected engineer pride in their work. These weren't just temporary structures. Each bridge represented hours of dangerous labor, technical precision, and genuine craftsmanship, despite expedited construction. Operation Market Garden in September 1944 provided a dramatic test of Bailey Bridge construction under pressure. The Sun Bridge near Eindhoven, destroyed by Germans just as the 101st Airborne Division arrived, needed immediate replacement. Captain Harold Young's Royal Engineers constructed a 180-foot double-double Bailey in 11 hours, allowing XXX Corps armour to advance toward Arnhem. The bridge's rapid construction illustrated how thoroughly Bailey techniques had been mastered. 11 hours for a complex heavy-capacity span under combat conditions represented remarkable achievement. The Rhine crossings in March 1945 showcased American engineer capabilities at their peak. Multiple armies crossed simultaneously at different points. Each crossing required bridges built quickly under German observation and fire. The 51st Engineer Combat Battalion built a heavy pontoon bridge at Remagen in 27 hours. The 291st Engineer Combat Battalion constructed an M2 steel treadway in under 30 hours, while under enemy artillery fire. At Oppenheim, engineers completed a heavy pontoon bridge within 24 hours of the initial crossing. At Rees, the massive 1,803-foot Bailey Bridge represented engineering at its most ambitious. The sheer scale challenged even experienced crews. 227 truckloads of components required careful orchestration. Each panel, transom, stringer, and chess had to arrive in correct sequence. The Royal Canadian Engineers managed this complexity while working through fog thick enough to obscure the far bank and German artillery that intermittently shelled construction sites. They completed it anyway. 2 days from start to finish, the bridge stood as testament to what systematic preparation could accomplish. Between D-Day and VE Day, Allied forces constructed over 2,000 Bailey bridges in northwest Europe. Total length exceeded 40 miles. American forces, after licensing the design in 1943, manufactured over 200,000 tons of Bailey bridging. This industrial-scale production meant engineers never lacked materials. Damaged bridges could be repaired immediately with spare panels trucked forward. New bridges could be built anywhere, any time, limited only by available labour and time. The 1139th Engineer Combat Group's record exemplified systematic excellence. Supporting Third Army's rapid advance, they built 119 tactical bridges, 39 exceeding 200 feet. Their 1,896-foot floating Bailey across the Rhine represented the longest tactical bridge built in the European theatre. They accomplished this while maintaining roads, clearing mines, demolishing obstacles, and performing countless other engineer tasks. Bridge building was just one mission among many, yet they excelled at it because training made the complex routine. German commanders consistently underestimated Allied bridging capability throughout the war. Early intelligence reports from 1943 dismissed accounts of rapid Bailey Bridge construction as exaggeration or misidentification. German engineering doctrine assumed temporary military bridges required days to build and couldn't match permanent spans for capacity. The Bailey violated both assumptions. By 1944, German Defensive Planning Incorporated adjusted expectations, but military thinking adapted slowly. Even late-war German documents reveal officers still surprised by how quickly bridges appeared. The captured German 15th Army Headquarters report from September 1944 documented this bewilderment. Enemy bridging capability exceeds all previous estimates. Bridges rated for heavy armour appear within 24 hours of arrival at demolished crossings. Defensive strategy requiring bridge destruction to delay advance no longer effective. Recommend revised doctrine assuming bridge replacement within 48 hours maximum. General von Vietinghoff's assessment proved prophetic. Destroying bridges no longer guaranteed delay. American engineers would appear, Materials would arrive in pre-positioned stacks, and bridges would rise with mechanical inevitability. German forces adapted by mining far banks, destroying approaches, and establishing anti-bridge fire positions. These tactics complicated construction but rarely prevented it. Engineers worked under fire, took casualties, and built anyway because doctrine demanded it and training enabled it. Japanese forces in Burma learned similar lessons. After encountering Bailey bridges repeatedly, Japanese commanders adjusted defensive doctrine. A captured operations manual from 1944 instructed units: British floating bridges appear overnight. Destroying river crossings no longer ensures delay. Plan defensive positions assuming bridge replacement within 48 hours. This represented fundamental shift in military thinking forced by Allied engineering capabilities. The cost-effectiveness proved as revolutionary as construction speed. A traditional military bridge capable of carrying 40 tons cost approximately £50,000 sterling in 1941. A Bailey bridge of the same capacity cost £6,000. Construction time dropped from days to hours. Labour requirements decreased from specialised engineer detachments to general engineer battalions with basic training. Casualty rates during construction fell below 5% compared to 30% for traditional bridge building under fire. American industrial capacity amplified these advantages. By 1944, women comprised 40% of Bailey Bridge production workforce. Over 650 firms in Britain manufactured components. 300 American manufacturers joined production after 1943. Quality control remained remarkably consistent despite dispersed production. Rejection rates stayed below 2%. Every panel manufactured in Detroit fit perfectly with panels from Pittsburgh, Cleveland, Chicago, or Birmingham. This interchangeability eliminated field compatibility problems that plagued other military equipment. The strategic impact extended beyond individual bridges. Allied commanders planned operations, assuming rivers wouldn't stop advances. This confidence influenced campaign design at the highest levels. General Eisenhower ranked the Bailey Bridge alongside radar and heavy bombers as three most important technical developments shortening the war. His assessment reflected genuine strategic value. Radar enabled all-weather operations. Heavy bombers destroyed German industry. Bailey bridges maintained offensive momentum regardless of terrain. Field Marshal Montgomery's evaluation proved equally definitive. Bailey bridging made an immense contribution towards ending World War II. As far as my own operations were concerned, with the 8th Army in Italy and with the 21st Army Group in Northwest Europe, I could never have maintained the speed and tempo of forward movement without large supplies of Bailey bridging. Without the Bailey Bridge, we should not have won the war. This wasn't hyperbole. Montgomery commanded armies that crossed dozens of major rivers and hundreds of minor waterways. Each crossing required bridging. Bailey bridges provided that capability reliably and repeatedly. The human cost savings mattered as much as operational advantages. Traditional bridge construction under fire resulted in appalling casualties. Engineers working exposed on scaffolding, moving heavy components with inadequate cover, spending days at dangerous sites. Bailey bridges reduced this exposure dramatically. The launching technique meant most work occurred on the friendly bank under covering forces. Construction speed meant less time vulnerable to enemy fire. Modular design meant damaged sections could be replaced without exposing crews to prolonged danger. Thousands of engineers survived the war because Bailey bridges kept them alive. The casualty reduction from 30% to 5% represented lives saved. Families that would have received death notifications instead welcomed sons, husbands, and fathers home. The engineering efficiency that shortened construction times also protected the men performing the construction. This humanitarian dimension of the Bailey Bridge's success often gets overlooked in discussions of military effectiveness, but the engineers who built the bridges understood it intimately. The ripple effects extended throughout Allied armies. Infantry trusted that bridges would appear when needed. Armour commanders planned deep penetrations, knowing river crossings wouldn't stop them. Supply officers scheduled logistics, assuming bridges would support heavy transport. This confidence at every level enabled aggressive operational planning. Commanders took risks they might otherwise have avoided because engineer capabilities made those risks manageable. The 11th 139th Engineer Combat Group's experience illustrated these dynamics. Attached to 3rd Army's 20th Corps, they supported some of the war's most rapid advances. General Patton's famous 48-hour reorientation during the Battle of the Bulge succeeded partly because engineers kept bridges operational and built new ones as needed. When 3rd Army pivoted 90 degrees and moved 100 miles in 48 hours, engineer units moved with them, bridging rivers on the fly and maintaining supply routes. The 371st Engineer Construction Battalion's Wesel Railway Bridge reconstruction demonstrated engineering at its most ambitious. 1,751 feet long, 2,140 tons, completed in 10 days. Railway bridges required more precise alignment than highway spans. Heavier structural members, stricter tolerances. Yet they built it in a time frame that astounded even Allied observers. The bridge carried military traffic for the war's final weeks, then continued serving for 7 years afterward. Remarkable longevity for temporary military construction. By war's end, over 700,000 Bailey Bridge panels had been manufactured, weighing 500,000 tons. This represented over 200 miles of fixed bridging and 40 miles of floating bridge capability. The scale of production matched the scale of need. From Tunisia to Burma, from Sicily to the Rhine, Bailey bridges carried Allied armies to victory. Each bridge represented specific men, specific skills, specific moments of dangerous work performed under pressure. Donald Bailey, knighted in 1946, remained modest about his achievement. When honoured, he responded, "I just drew some lines on an envelope. The brave men were those who built the bridges under fire." His humility was characteristic but understated the design's importance. The lines he drew transformed military engineering. The bridges built from his design shortened the war and saved countless lives. The post-war legacy proved enduring. Bailey bridges served in Korea, where United Nations forces built over 300. The design influenced all subsequent military bridging. Modern systems still use Bailey's modular panel concept. In civilian applications, Bailey bridges provided emergency infrastructure worldwide. The 1975 Tasmania Bridge, spanning 2,585 feet, demonstrated the design's scalability. India's military maintains 4,000 tons of Bailey bridging, using it at altitudes exceeding 15,000 feet during the 1999 Kargil conflict. The fundamental principle Bailey established remained revolutionary. Complexity was optional. Previous bridge designs pursued engineering elegance through sophisticated structures requiring specialized construction. Bailey inverted this thinking. His design achieved sophistication through simplicity. Anyone could build a Bailey bridge given basic training and adequate materials. This democratization of complex construction proved more valuable than any amount of engineering refinement. American riggers built Bailey bridges in 4 hours, not through individual genius but through systematic preparation. They trained until muscle memory replaced conscious thought. They used equipment manufactured to tolerances, ensuring universal compatibility. They followed doctrine refined through thousands of combat deployments. They worked within a system designed to make the difficult routine. This combination of training, equipment, and doctrine allowed ordinary soldiers to accomplish extraordinary feats. The title's question, "Why American Riggers Crossed Every River First?" has a multi-layered answer. They crossed first because Bailey bridges gave them tools that worked. They crossed first because training made them proficient with those tools. They crossed first because American industrial capacity produced enough materials to bridge every obstacle. They crossed first because doctrine emphasized speed and aggressive momentum. They crossed first because systematic preparation made seemingly impossible construction times routine. But the deeper answer lies in the transformation of military engineering from craft to industrial process. Bailey's design eliminated most prerequisites for bridge construction. American training made construction mechanical and repeatable. Industrial production provided unlimited materials. Doctrine emphasized relentless forward movement. When these elements combined, bridges appeared wherever needed with stunning reliability. German and Japanese forces couldn't match this capability, not because their engineers lacked skill, but because they lacked the systematic approach, making rapid bridge construction routine. The bridges that rose across Europe and Asia in 1944 and 1945 represented more than engineering excellence. They represented a fundamental shift in how military forces approached obstacles. Earlier armies stopped at rivers until engineers laboriously constructed crossings. Allied armies expected rivers to delay them briefly while engineers worked their systematic magic. This expectation, backed by consistent performance, changed operational planning and strategic possibility. Consider the cumulative effect. 2,000 Bailey bridges in northwest Europe alone, 3,000 in Italy, hundreds in Burma. Each bridge enabled continued advance, each crossing maintained momentum. Each day of sustained offensive pressure wore down enemy forces lacking equivalent mobility. The strategic advantage compounded across months, until German and Japanese defensive options narrowed to inevitable defeat. The men who built these bridges did so under conditions most civilians couldn't imagine, waist-deep in freezing water while artillery shells exploded nearby. Working in complete darkness with enemy positions visible across the river, assembling bridges while comrades died from enemy fire or construction accidents. They did this work not once but dozens of times as their units moved from river to river. The courage this required was extraordinary, yet it became routine because training and doctrine made extreme danger normal. Private First Class Anthony Benedetto's observation about bridges appearing overnight like magic captured the infantry perspective. From their viewpoint, engineers performed near miraculous work. Infantry went to sleep facing an impassable river and woke to find a bridge strong enough for tanks. This seeming magic was actually systematic preparation and flawless execution, but to soldiers benefiting from it, the distinction hardly mattered. The bridges worked. Advances continued. Wars were won. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.